One of the most popular times to go rock hounding on the Great Lakes is after dark. There's a good reason for that. It's not because Midwesterners are idiots who think that finding rocks after dark is easier. It's because a lot of us come out to the shore equipped with a specialized flashlight like this that makes some stones light up like so. These go by several names, the most common of which is Yooperlite, sometimes also called Yooper stones or variations on that, sometimes also called fluorescent sodalites. So what are they? Why do they glow the way they do? We're going to be taking a deep dive into the science today, as well as talking about where they come from, where you can find them, and the best tools for finding them yourself. So join me as we take a deep dive into Yooperlites on Craig the Geologist After Dark. After Dark. I hope you're enjoying the ridiculousness of this segment as much as I am. I'm going to keep rolling with that whole After Dark thing for at least a few more episodes of this. So before we dive into the science of Yooperlites, let's talk a little bit about their history. And there's not much to that history. Yooperlites were first discovered in 2017 by a gentleman named Eric Rintamaki. And this isn't a scientist who was laboring in a lab. Eric Rintamaki was just a dude with a UV flashlight on the shores of Lake Superior. Apparently the first one to bother taking a UV flashlight out onto the shores, and discovered, hey, some of these rocks glow orange. What's the deal with that? He very wisely, to his credit, sent a sample of the rock to a gentleman named Sean Carlson. Sean Carlson was a very good friend of mine who unfortunately passed away just about 2 years ago. But Sean took the rock samples and he analyzed the mineralogy of it and identified the glowing mineral as sodalite. And so that's how we discovered what Yooperlites are. He didn't do a whole rock analysis of it. He didn't determine the rock type scientifically. He just kind of looked at it and said, it looks like a syenite. And so they became known as fluorescent sodalite bearing syenites. That is, syenite rocks that have fluorescent sodalite in them. Now, the actual situation is quite a bit more complex than that. We'll talk about that in a little bit. But it's a brief history, because before 2017, we didn't know about these rocks on our shores. And since then, it's become a really big thing. People go nuts for it. And some folks in the fluorescent community take it to a real extreme that I personally get a little wary of. But our monkey minds are just attracted to things that glow in the dark. We love it. And I can't fault people for that. I love it too. And I've got a small collection here myself. The next burning question that needs to be answered before we can really dive into the science of them is, what do we call these rocks? Because there is a lot of controversy about that in the rock hounding community, and an insane level of paranoia and conspiracy theory in some of the fluorescent communities. So let's settle that. Eric Rintamaki named these Yooperlites, and the name comes from the fact that folks in the Upper Peninsula of Michigan, the UP, are referred to as Yoopers. And so he just thought it kind of a cutesy name for a mineral that lights up. A lot of minerals, like sodalite, for example, end with light, so he called them Yooperlites. However, he then went and he trademarked that name. Now, what does that mean? There's a lot of folks who tell you you can't ever use it. Eric Rintamaki will sue you in an instant, in a heartbeat, if you use the word Yooperlite. Well, that's not true. You can agree or disagree with his trademarking of the name. I personally disagree with it. Sean Carlson strongly disagreed with it, as the guy who actually identified the minerals in Yooperlites. I wanted him to write an article for my magazine about it, and he then went on a 20-minute tirade about how he wished he had never done anything with the Yooperlites in the first place. And after listening to him for 20 minutes, I'm like, I can't publish that. How about you write about something different? But what does it mean that it's trademarked? It means you can't sell under the name Yooperlite. So if you have a flashlight, you can't sell it as a Yooperlite flashlight. Only Eric Rintamaki can. And as my understanding is, if you're selling these rocks, you can't sell them as Yooperlites. He has the name trademarked, which trademarking a name of a rock, kind of crazy, but you know, it was approved by the US Patent or Trademark Office. I'm not a lawyer. It is what it is. However, if you're just a guy or a gal using the word Yooperlite, there's nothing wrong with that. For example, my name is Craig McLaren. I can talk about Big Macs all I want. I can talk to you about the sandwich. I can describe it. I can tell you I'm going out to eat a Big Mac this afternoon. I love Big Macs. Big Mac, Big Mac, Big Mac. Whatever. That's great. This video is not going to be taken off of YouTube for my having said the word Big Mac. However, if I open a McLaren's burger joint and start selling Big Macs myself, McDonald's lawyers are going to come down on me hard. And so it's a little bit the same with the Yooperlite name. You can call them Yooperlites. If you're a store owner selling things under the name Yooperlite, then you got to be a little bit more cautious. But for all the rest of us normal folks who aren't doing that, use the word Yooperlite all you want. A lot of folks use the word Yooperstone because they're paranoid about using the word Yooperlite, or because they're shop owners who are justly concerned about using the word Yooperlite. Yooperstone, Yooperrock, whatever, it's all good. Some people love to flex their knowledge and say they're not Yooperlites. These are sodalite bearing cyanites. Sometimes they say it backwards because they don't really know what they're talking about. I've had plenty of people tell me, hey, these are cyanite bearing sodalites. I'm like, you got it backwards. The cyanite is the rock and it contains sodalite. But while that's right, it's not really accurate. It's actually less accurate than calling them Yooperlites, because there's actually a lot of variability in the rocks themselves. Not all sodalite glows. Not all of these rocks are cyanites. If you want to get really pedantic, you could say that these are not Yooperlites. These are disodium caged fluorescent sodalite bearing granitoids of an approximately monzocyanotoidal composition. That's kind of insane though. I mean, the worst thing you could do in rock hounding, in my opinion, is get super pedantic for absolutely no reason. So I'm going to be referring to these as Yooperlites tonight. And I'm going to be referring to the rocks as Yooperlites. I will be referring to the mineral that glows in them by their proper name as sodalite. All right, let's begin by discussing the mineral in the rocks that glows. You know, without that mineral, no one would care about these rocks. Certainly nobody cared about them before 2017 when we discovered they were fluorescent. So the mineral we care about is sodalite. And I am just going to put the name right up here instead of writing it on the board, because as demonstrated in previous videos, I write very slowly. Sodalite has a pretty much impossible to remember composition of. It is feldspar, or more accurately, a feldspathoid. That is, it is a feldspar or feldspar adjacent mineral. And feldspars tend to be kind of trash can minerals with variable compositions. And sodalite is just part of that group. Now, sodalite is famous for its bright blue color. It's gorgeous. It's a deep blue. And here, I'm going to show you some pieces in the daylight here. These are your classic royal blue, gorgeous sodalites. This is what people think of when you say the word sodalite. Folks picture this deep, rich blue color. It's what sodalites are really known for. These pieces came from Bancroft, Canada. That's in the Great Lakes region, not on the Great Lakes themselves. You won't find samples like this on the shorelines, but it's in the region. It's pretty localized to the Bancroft area though. You won't find it outside of there. This is a piece here that just has a single streak of sodalite running through it, and what is otherwise probably a mostly feldspar rock. When we zoom way in on these, you can see that it has a very glassy look to it. It has a very glassy fracture to it. It has a conchoidal fracture. And so it has a lot of similarities with quartz and its general crystalline appearance when it's broken, but it's deep blue. Yooperlites, however, don't have that bright blue variety of sodalite. The sodalite in the Yooperlites is white, gray, milky colored. It's colorless. It's dull. We didn't even know the cyanites in these rocks on our shores had sodalite in them because, well, nobody bothered to test it. And when you pick it up and look at it, there's no reason to think it's got sodalite in it. But why aren't the sodalites that are in our Yooperlites dark blue? The dark blue sodalites are often at least a little bit fluorescent. Let's take a look here at how some of these deep blue sodalites light up under UV light. They do shine for the most part, but not very brightly. It's kind of an internal weak glow that they have. It's certainly not bold and bright like the Yooperlites. And this sodalite doesn't shine at all under UV light. There's no fluorescence whatsoever. Here's a little comparison under daylight. You can see some very weak UV fluorescence over there, but compare that to the Yooperlites and see how bright they are. Now this is a fun piece. I actually discovered sodalite in this just while I was filming. It's a piece I picked up from Bancroft because it has beautiful biotite crystals in it. Take a look at those. They're just gorgeous. But the rest of this I just assumed was a white feldspar of some sort, and for the most part it is. But with UV light shining on it, there is definitely a little bit of colorless sodalite inside. Here we're taking a look at the deep blue sodalites after dark. This is the white one that I discovered some sodalite in. But over here, these are the deep blue ones. You get a little bit of UV fluorescence, not much. Some pieces, like that, none whatsoever. But compared to the Yooperlites, it's really minimal. But as you can see, they're not wildly fluorescent. They're not nearly as fluorescent as the Yooperlites are. And some of the material isn't fluorescent at all, despite seeing that deep blue color that obviously makes it sodalite. But why is that? Why are the Yooperlites super boring under regular visible light and the other sodalites absolutely gorgeous, but the gorgeous sodalites barely shine under UV light, and the Yooperlites sodalite just lights up these crazy bright orange fireworks of color? Well, it comes down to the crystal structure of the sodalite. So let me draw a picture of a sodalite cage for you, and I'll fast forward it while I draw just to make it a little bit quicker. So what I've attempted to draw there is a cage of sodalite. This is kind of what happens. The actual structure for it is a little bit different. And I will post a picture of that in just a moment here. But this kind of simplified version of the cage we're looking at here, you've got your cluster of mineral, and they're bonded together, but they leave an empty space in the center. And in that empty space, you tend to have sodium or chloride ions. But other atoms can substitute in there also. And in fact, there are a lot of studies on sodalite used for, looking into the sodalites used for water purification, for removing heavy elements from water, for removing radioactive and other substances. It tends to grab onto other materials and trap them in this cage structure, One of the more common things it traps under natural conditions is sulfur. And the type of sulfur matters. Tetrasulfide and trisulfide are the two most common ones. And both of those, tetrasulfide, which is 4 atoms of sulfur all hanging out together, and trisulfide, 3 atoms of sulfur all hanging out together, those create your deep blue sodalites that just look beautiful under visible light. But they don't fluoresce. You can also get disulfide trapped in there. Disulfide does not create those color centers. You don't get the blue color in your sodalite anymore. Now you have colorless, boring sodalite that looks like nothing under visible light. But disulfide, when trapped in those sodalite cages, those electrons are shared with the surrounding cage. They're kind of pulled into a position that now when you hit it with UV light, you get fluorescence. And so that's the reason why I use that crazy complex term, disulfide caged sodalites earlier. That's what you've got there. Most sodalite fluoresces a little bit because there's usually at least a little bit of disulfide caged up in your sodalites. Even if it's a deep blue sodalite where it's mostly trisulfide or tetrasulfide, you get a little bit of disulfide in there to give it a little bit of glow. Not always though, as you see in one of my samples. But yeah, disulfide, you get no color with that, but you get fantastic fluorescence. Now, in a previous episode of Craig the Geologist After Dark, I talked about the quantum mechanics of fluorescence in detail. So I'm just going to touch on that very briefly here. We're going to talk about these disulfide atoms, and I'm going to draw the fictionalized planetary style model of an atom, where you have your protons and neutrons in your nucleus here, and then you have your electrons orbiting out here. Now, if you want that detailed description of how fluorescence works, I would strongly encourage you to go check out this video. It's only a few minutes long, really. And it'll take you in depth about what's going on. But the short version here is the UV light strikes the sulfur atom. The electrons on that sulfur atom have been pulled by the sodalite cage into just the right position, that when UV light of a very specific wavelength comes in and strikes it, the electrons jump up in orbital. Whoop. That is a really bad drawing there, but pretend it's good. Use your imagination here. It jumps up in orbital. And it's unstable in that orbital. So as soon as it jumps up there, it comes right back down. And as it comes back down, it has to release a photon of energy because it's jumping from a higher energy orbital to a lower energy orbital. The energy has to come somewhere. It shoots off a photon, and that's the visible light we see. And the distance it jumps from one orbital to the next is the amount of energy it lost. That relates directly to the wavelength of light, and that is the color that your eyes see. And so it's an amazing thing that with a UV flashlight and a fluorescent material, your eyes can actually watch a quantum mechanical process happening in real time. It's pretty amazing, because if you can't witness quantum mechanics with your naked eyes in pretty much any other way, at least not directly the way you can with fluorescence, it's pretty awesome. All right, I'm going to erase this model just because I hate the way it looks. We're done with it now anyways. I would strongly encourage you, if you haven't watched the previous video on fluorescence, check it out. Next, let's talk about the cyanites and their variability a little bit. But for that, we need daylight. We need a little bit of visible light. So come with me. So give me your opinion here. You can type it into the comments if you want, shout it at your screen, your choice. But if this weren't a video on Yooperlites, and if I had just come to you with a handful of rocks that look like this, would you look at those and say, hey, these are all the exact same rock type? My guess is you would not. And you'd be right. You don't have to be a geologist to look at these and say, these are some very different looking rocks. But they are all Yooperlites. They all have that fluorescent sodalite that glows so brilliantly under UV light. Let's pause this video for just a moment and make some quick observations about these rocks. Take a look at the right side of the screen and top center. You see some very white colored rocks with just a little bit of black mineral mixed in. In the lower right hand corner, you see some grayish rocks. These are pretty finely crystalline, but you can still see the crystals in them. And then you also have some chunkier looking rocks, kind of just left of center, pretty light colored. But you also get these dark gray, dare I say black rocks that are also Yooperlites. So what's going on there? Well, we can see that the composition is not uniform. These did not come from a single rock unit with a uniform composition. In fact, it probably came from several different rock units in Canada. Now, there is color variability in syenites. Syenites are often red, but very often they are white and light gray as well. And so when Sean Carlson looked at the Yooperlites he was sent, he probably saw those light colored rocks and said, yeah, that's a cyanide. But taking a look at those dark grays and those blackish rocks, that really doesn't match up well with a pure cyanide. There are variations on it in the whole granitoid spectrum. Monzocyanite, Foyd cyanites, but you really, as a geologist, would not look at one of these black colored rocks and be like, oh yeah, that's a cyanite. Now, I haven't done a spectroscopic analysis of all the mineral constituents of these. I'm just eyeballing these, but I'm telling you right now, if you're gonna call them all cyanites, you're more wrong than calling them all Yooperlites. If Yooperlite is a term to describe rocks that glow under UV light in a certain way, these are all Yooperlites, but they're certainly not all cyanites. Now, these rocks are close to being cyanites. They're cyanite adjacent. They're in the realm of cyanites. So you could say that in the same sense that rocks with a granitic look to them and a granitic texture that aren't technically granites compositionally are granitoids. You could say the same thing about these in proximity to being cyanites. They're cyanitoids. But there's certainly a range of compositions and different rock types mixed in with these in that cyanitoidal group. Let's have a close-up look at some of the UV characteristics of these Yooperlites. We're beginning here with a overall rather grayish Yooperlite rock with plainly visible crystals in it. And you can see it's the white zones in that rock that light up. Here's another example, very similar. And amidst all those black speckles, you have some sections of white mineral lighting up. In fact, in this rock, the sodalite is a slightly off red color, you might notice, but generally it's going to be colorless. Here's another one, and notice you get pretty big sections of sodalite in this one. They really kind of clump together and form larger crystals in this. But again, it's only the white to colorless parts that glow, never the black. Here's another case, and this looks like a huge piece of sodalite in this, and relative to the size of the rock it is, but it's actually a very tiny Yooperlite. You find them in every conceivable size on the shorelines. This one has some sodalite, probably mixed with some feldspar, deeper within the rock that's causing a big part of it to glow. Here we're going to see a bit more of the same. Let's shine that UV light over it. Beautiful. Now, when you go to rock shops, you'll sometimes see posters where they name all the different Yooperlite patternings, all the different sodalite patterns that you get in it. As a geologist, we don't bother with that kind of nonsense. But you do get a lot of different shapes, and people who can recognize animals and all sorts of beautiful shapes in the clouds, they come up with great names for hundreds of varieties of Yooperlites like this. Have a look at that. That is a lot of sodalite in that one section there. And it's making up a significant part of the rock just on the tip. But you'll notice the sodalite doesn't run throughout the entire rock. And this is a pretty small piece also. Now we're taking a look at the dark gray to blacker rocks. Now, sodalite is never dark colored. I mean, it could be blue, but it's never dark gray or black. So what you're seeing in this are the tiny little specks of colorless sodalite that you mostly can't see with your naked eye shining up in these darker rocks. It's mixed in. It's keeping that black rock from being totally black. It's giving it that kind of speckly gray look. And we're seeing it light up in that very diffuse beach sand pattern. Rocks like this, if I was walking out during daylight, I would never suspect it of being a Yooperlite, not without shining UV light on it. Now here is the case where you have a grayish rock with visible crystals, but you still only get the very fine, diffuse sodalite scattered like beach sand through it. By the way, I keep showing these Yooperlites under visible light conditions. What do they look like at night? Well, the same way they do in the daylight with a powerful UV light, but more so. And of course, you're never going to be able to find these Yooperlites on a beach, no matter how powerful your UV flashlight is, under direct sunlight, because the color just will not show up. It's too bright. You can only hunt for these things at night. You can look at them on your desk close up, with some ambient light around. But if you're on a shoreline during the day, you have a 0% chance of ever finding a Yooperlite with your UV flashlight. It has to be at night. All right, now time to answer the practical questions. Where are they from? Where do we find them? How do we find them? First of all, where are they from? If you look it up online, you'll find out that they come from the Coldwater Alkaline Complex on the North Shore of Superior in Ontario. However, that complex is very small in area. And while I don't know a great deal about that complex, looking at the rocks themselves, the Yooperlite selection, there is a lot of variability. And so I suspect that in truth, Yooperlites come from quite a few different areas, not just a single complex. But I would agree that the Coldwater complex is responsible for a majority of what you find in some areas. You can also find some on Lake Ontario, and those probably came from a source near to Montreal in Quebec. The distribution of Yooperlites across the Great Lakes region are controlled by the flow direction of the glaciers from the Laurentide ice sheets back about 10,000 years ago. As you will hopefully already know, the Great Lakes region was carved up by the glaciers. As they moved south, they bulldozed the earth, dumping a lot of Canada onto the shores and inland areas of the Great Lakes region. And that carving up of the earth brought the Yooperlites from their source rocks in Canada and dumped them in Michigan and the other Great Lakes states and the places where you can find them. You can't find them everywhere though. The glaciers flowed in very specific paths. They took preferred pathways. It wasn't just one monolithic sheet moving southward. There were paths that the ice sheets took that in some places the ice was moving faster, in other places slower, in various directions. And geologists have actually done a very good job of mapping that out. And when you compare the distribution of Yooperlites with those maps, you can kind of trace them back to the cold water complex and the area around there, at least for the Yooperlites in Michigan and Michigan adjacent areas. So where can we find these Yooperlites? Well, thanks to the flow direction of the glaciers, if you're in the southern Great Lakes region, you can find Yooperlites along the shores of Lake Michigan. You can find far more up along the shores of Lake Superior due to the proximity to the source rocks in Ontario. You don't tend to find any along Lake Huron in my experience. And you have to be a little bit careful about that now too, because there was a news story recently about Harrisville State Park, which is just north of me. Yooperlites had been found and it became a big regional news story. And after the news came out, a guy I knew and used to be friends with was laughing with me and said, "Oh yeah, I seeded the beach there. I thought it would be good for tourism, so I went there with a bucket full of Yooperlites and just scattered them across the shore. And now they've got a Yooperlite program at the state park where they, loan out UV flashlights for tourists and they all hunt. There's nothing to be found there. And there are a lot of folks who are just troublemakers. They laugh about seeding the beaches with foreign rocks from New Jersey that light up and laugh at all the confusion it causes. So you got to be a little bit careful about new claims about places where Yooperlites and fluorescent minerals have been found along the Great Lakes region, because there are folks who go out there with a bucket full of rocks and try to cause problems. So in places where I know seeding hasn't happened, I have found no Yooperlites whatsoever along the shores of Huron. And keep in mind, though, that especially in the area around Lake Michigan, Lake Superior, where you do find Yooperlites, while the shoreline is where everybody goes to find them, there's nothing terribly special about the rocks on the shoreline, except for the fact that the waves have washed away all the soil and made it super convenient for you to see the rocks. The same rocks that are on the shore are the rocks that cover the entire inland area. They're underneath all of the forests inland. They're in all of the farmers' fields. They're in every gravel pit. It's the same glacial material on the shores that cover the whole region, Wisconsin, Minnesota, Michigan. It's all the same glacial material. And you can find Yooperlites inland. It's just harder because they tend to be underneath a lot of soil. So assuming you're going to go to the shore to collect Yooperlites rather than walking through the forest, which I do not recommend, please do not go rock hunting in the forest after dark. It's just a bad idea for several dozen reasons. You want to make sure you're going out with the right tools. And the most important tool for you to have out there is the right flashlight. You want a long wave UV light, and you want it to be 365 nanometer wavelength. Most of the flashlights that you find online for super cheap are 395 nanometers. Now that sounds real close. 395, 365, isn't that close enough? The answer is no. and I went through a number of bad, cheap UV light purchases from Amazon before I learned my lesson. I bought some 395 lights thinking they'd be good enough. They weren't. I bought some of the cheapest 365 nanometer flashlights. The specs looked great on them. The dark beam was one of them, and they were terrible. They were just as bad as the 395 lights. And so I finally got myself a lumen shooter, which is basically, in my experience, the cheapest good flashlight there is. I think I bought mine for about $45 when it was on sale. I think it's usually about $60. And it does a great job. There are more expensive brands of flashlight that will run you up to a couple of $100. They are better than the lumen shooter. Are they worth the price? That depends on you. For me, no. For some people, yes. In my experience, comparing the lumen shooter against some of the more famous brands that I won't mention by name for various reasons, they tend to light up the ground maybe 50% better, but they cost 3 times as much. So, for me, it's not worth it. For some people, it is. But you want at least $40 or so, 365 nanometer wavelength UV light. And filtered UV. Make sure it's got a filter on it. That'll help with the quality of the light you're getting out of it. Anything cheaper than that, don't waste your money. You're not getting anything out of it. And, you know, it's up to you. If spending a couple $100s on a light means nothing to you, go for it. You'll enjoy it. But, you know, if you got to pinch pennies like most of us, $50 light will do the trick and will work just fine. All right, enough of me telling you about the differences. Let's take a look at the differences. Now, the first light I'm going to be showing you is a generic off-brand 395 nanometer 30 LED light. Next one is the dark beam from Amazon. Now, you will hear a lot of people telling you this is a perfectly good light online, that it works. But we're going to take a look at how it actually works. I think you will be unimpressed. I certainly was. Next up, I have a small pen light. It's a FS Hunter Mini. Now, I can't recommend buying these because you got to hunt down a guy and strike a kind of shady online deal with them through private messaging. I was gifted this one, but it does work very well, frankly. And the final light I'll be using in this demo is my favorite. This is my go-to when I'm out Yooperlite hunting. This is the Lumen Shooter S3. They do make an S5. The number is the number of LEDs it has in there. So the S3 has 3 UV LEDs. The S5 has 5. This is what you see when you're using the 395 nanometer 30 LED flashlight. There is a huge amount of purple light. Now, you do see some orange glow, not very much though. Only from a couple of the Yooperlites do you see anything really. And look at the amount of contaminant purple light in there. UV light is supposed to be invisible to your eyes. So the fact that you're seeing so much purple is just telling you how much contaminant light there is. You don't want that when you're out there. Now we're looking at the dark beam. As you can see, the dark beam does work. It is a 365 nanometer light, and you're not seeing all that purple contaminant light in there. Now, you can see it is rather dim though. There's not a whole lot of glow coming off of these Yooperlites, but it certainly seems to be a step better than having the wrong wavelength of light. Now we're using the pen light, the FS Hunter Mini. And despite it being a very small single LED flashlight, it is of a good quality. It is 365 nanometers. It is filtered, and it does hit those Yooperlites so brightly. What you won't see in this close-up demo is the Lumen Shooter S3 because it is too powerful a light for these real close-up shots. But now, let's go outside and have a look from 5 feet away what these lights look like when you're shining them on the Yooperlites. This is the generic 395 nanometer wavelength 30 LED flashlight. As you can see, there's a whole lot of purple over there, but not very much actual orange glow from the Yooperlite. Now I'm getting out the dark beam, and believe it or not, I am shining the dark beam directly on the Yooperlites. Dark beam has to be the most accurate name I've ever heard for this flashlight because you can't see anything. If you're real close up at your table, you can see the Yooperlites glow. But if you're out hunting, boy, you better be a couple of inches away from those rocks. Now I've got the FS Hunter Mini, the small pen light, and you can see it is doing a good job. Almost no contaminant light visible, and we're seeing those orange Yooperlites from 5 feet away. Now, getting out the Lumen Shooter S3, you're going to see something very similar, but it's going to be brighter. It's a much more powerful light. You do get a little bit of light visible there just because there's so much shining out of this light. A small amount of visible light does reach your eyes. Now let's compare the small pen light to the powerful S3. You can see there is a difference. It's not a huge difference, but it does make a bigger difference the further away you are from the rocks. Finally, let's compare a lousy flashlight of the wrong wavelength, the 395 nanometer flashlight, which boasts a powerful 30 LEDs, to the Lumen Shooter S3, a good quality flashlight of the right wavelength and filtered. The difference is stark. Go out there with the right UV flashlight. Don't go ultra cheap, and make sure you're buying the right wavelength of light. The UV light is really the only thing you need out there. There are a few other things that you will want. You will want a regular flashlight because at some point you're going to need to see where you're going. I also highly recommend going out with some glow sticks or something that glows in the dark and marking the path to your car. Because there have been a number of times when I've gone out and I'm like, oh yeah, I'm going to remember where the trail to the parking lot is. I can find my way back. And then I end up wandering back and forth up and down the beach for about an extra 20 or 30 minutes before I figure out where my car is at. So laying down a couple of glow sticks to mark it, real handy. They're very cheap from Walmart. It's worth the $1 investment. Good water shoes, something you don't mind getting wet. You will, if you're like me, say to yourself, yeah, I'm not going in the water. I'm not going in the water. And then you're going to fall in the water. You're going to encounter a small stream you got to go past, and you're going to get wet. And I will also say this. I very often find the nicest Yooperlites in the water where people aren't already willing to walk. So shorts and some shoes that are okay to get wet. Highly recommend that. Here's a little something I forgot to talk about, but eye protection. Do you need it? Well, the answer is yes, no, and how nervous are you? Me, I wear eyeglasses that already have a UV protective film on them. And I only use long wave UV when I'm out hunting on the shores. And so the flashlights, as powerful as they are, don't tend to put much more UV on the rocks than the sun does. The only difference is we're doing it at night without any visible light. And so the reflection off of the rocks really isn't going to do very much eye damage. Now, that advice may change if you're out there every single night of your life for a couple of hours a night, and there are people who do that. Then you will probably want more eye protection, just like you'd want a UV protective film on your eyeglasses if you spend all day hiking under the hot sun. Also, if you're using shortwave or mid-range UV light to do fluorescent hunting of any kind, those wavelengths of light are far more damaging to your eyes and skin. So eye protection is recommended in those instances. But for the casual Yooperlite hunter who's just going out for an hour or two a year and using a long wave light and being careful not to shine it at or near their eyes, how nervous are you? That's the question. The special glasses aren't very expensive. They're easy to get. So, if you're worried about it, get them. But if you're worried that you're going to lose your vision after being out there for an hour with a black light, that's paranoia. You don't need to be worried like that. Honestly, that's pretty much all there is to know about the science of Yooperlites, where they come from, how they formed, why they glow the way they do, and how to find them for yourself. So get out there, good luck, and thank you for joining me on Craig the Geologist After Dark. After Dark.